I'm Yican from Peking University. I'm going to share with you about our recent work on synthesizing efficient memoization algorithms to solve combinatorial optimization problems. First, let me introduce the combinatorial optimization problems, short as COPs. COP is an important category of real-world problems. In general, it targets to find the best valid solution, where valid means that the solution should satisfy some user-provided constraints, and the best means that the solution should maximize a given objective function. For example, let's consider the classic 0-1 knapsack problem, where there are several items. Each item has a weight and a value. There is also a knapsack with a capacity limit. The goal is to choose a subset of items such that the total weight of the selected items does not exceed the capacity, and the total value of the selected items is maximized. Here we present a concrete example. There are 4 items whose weight and value is presented below. The capacity of the knapsack is 5, and the optimal solution is marked red. We can verify that the total weight of the red items is 5, which does not exceed the capacity of the knapsack, and we can find that the total value is 44, which reaches the maximum. So how to solve COPs? Maybe the first idea that comes into our mind is to apply exhaustive search, where we just try every solution and pick the best valid one. However, this is obviously too slow because the number of solutions is always tremendous. For example, let's consider the knapsack problem with n items. There would be 2 to the n solutions, which is exponentially large. To efficiently solve COPs, dynamic programming is a powerful and widely used technique. For 0-1 knapsack problem, its dynamic programming algorithm has a complexity n times c, where c is the capacity of the knapsack, which is much more efficient. Motivated by the importance of the combinatorial optimization problems and the dynamic programming algorithm, we propose a tool called SynMem that can automatically synthesize dynamic programming algorithms from logical description of COPs. At the input side, the logical description is written in a constraint modeling language, for example, Minizinc. In detail, the specification can be divided into 4 separate parts. First, the input part specifies all components to describe a problem instance. In the knapsack problem, we use n to represent the number of items, c to represent the capacity, and we use 2 arrays, weight and value, to represent the weight and value for each item. And in the right side, we show the parameter choice of a previously presented concrete example. Second, the solution part consists of all components to describe the solution. In the knapsack problem, we use the array P, where Pi represents whether to put the item I into the knapsack. If Pi equals 1, then we put the item I, and if Pi equals 0, then we does not put the item I. Third, in the constraint part, we impose constraints to the solution. In the knapsack problem, we make sure that the total weight of the selected items does not exceed the capacity C. And finally, in the objective function part, we will set up an objective function that maximizes the total value of the selected items. At the output side, we produce a top-down approach of dynamic programming, which is also termed as memoization algorithms. Generally, a memoization algorithm is in a recursive form. It decomposes a problem into several subproblems and recursively solves these subproblems. The key point that makes a memoization algorithm efficient is that during the recursively solving procedure, there are many pairs of subproblems that can be identified to be equivalent. For each equivalent class, we only need to solve one subproblem in this class, and the results of other subproblems in this class can be effectively reused. However, synthesizing a memoization algorithm is never easy. There are 2 major challenges here. The first, the memoization algorithms are always very large, and it is beyond the capability of the existing program synthesizers. And second, it would be very hard to verify whether such a large program is efficient or not. So there is an efficiency challenge. Our solution is that we propose a novel template of memoization algorithm that can tackle all previously proposed challenges. Moreover, our template is much more general than previous templates. And below, let's dive into some more details. To design a memoization algorithm, we need first to figure out the notion of subproblems. We find that the notion of subproblems can be extracted from the search tree of the exhaustive search. And in the right side, we present the search tree of the knapsack problem. It is organized in layers. The first layer is a root node. The second layer, we enumerate the value of P1. And in the third layer, we enumerate the value of P2. Below, we can see that there is actually a correspondence between the nodes in the search tree and the subproblem. At the root node, we can find that this subproblem is just identical to the original knapsack problem. Now suppose we have decided P1 to 0, and let's look at the right node. At this node of the search tree, since the value of P1 has been determined to 0, we can remove it from the solution part, and the solution part is just finding an assignment to the remaining P2, P3, P4 to Pn. And in the constraint part and the objective function part, we can replace P1 with its decided value 0. And we can find that this is exactly the COP that this subtree, the green marked subtree, is trying to solve. Suppose we further decided P1 to be 1. Now the remaining task is further changed. We just need to decide the value of P3, P4 to Pn, and we can further replace the value of P2 to be 1 in the constraint part and in the objective function part. In general, every node in the search tree corresponds to a subproblem. By enumerating the value of a new variable, a parent subproblem can be split into two child subproblems, and the parent subproblem picks a better solution from two child subproblems. However, unfortunately, these subproblems cannot be reused, and let's see why. To reuse between two subproblems, in principle, we need to make sure that these subproblems will produce the same answer. In this work, we consider three natural conditions of the equivalence of subproblems that can guarantee the same answer. In detail, two subproblems are identified to be equivalent if they share the same solution part, that is, the same set of variables in the solution part, and they have equivalent objective functions and they have equivalent constraints. Let's check the first condition. It can be satisfied by many pairs of subproblems. We can see that as long as two subproblems are at the same level of the search tree, this condition can be satisfied. They will have the same solution part. However, the second condition is rarely satisfied, and let's see why. Let's just consider two sibling subproblems where they assign different values to the variable P1 and the other variables are still undetermined. We can see that the objective function depends on the value of P1. In the left side, we assign 0 to P1, and there would be a term called value1.0. And in the right side, we assign 1 to P1, so there would be a purple term called value1.1. And this is different, and this makes the objective function to be different. Indeed, different subproblems assign different values to the enumerated variables, and thus there is little chance to satisfy the condition on equivalent objective functions. So, to make the objective function independent with the enumerated variables, we introduce the local objective function, LOF, and replace the original objective function with the LOF. For knapsack, the LOF is the total value of the to be selected items. And we need to make sure that the replacement does not affect the answer, and it preserves the order of the solutions. After applying the LOF, the objective function of each subproblem become independent with the enumerated variables. So as long as two subproblems have the same solution part, they share equivalent objective function. Note that we also need an updating function for LOF to obtain the best solution of the parent subproblem from those of child subproblems. Finally, let's check the equivalent constraint condition. This condition can be generally checked via constraint solvers, but it would be very costly. Thus, we introduce the memoization partition function, MPF. We need to make sure that if two subproblems with the same solution part and they have the same MPF value, then they share this equivalent constraints over variables. For knapsack, this function is the total weight of the selected items. After applying MPF, we just need to check whether two subproblems have the same solution and that they have the same MPF value, which is much easier to check. We also need an updating function to efficiently obtain the MPF value of the child subproblem from the parent one. In summary, we have the following formula for memoization algorithms. We find that memoization algorithm is just the exhaustive search plus two functions, LOF, MPF, and together with their updating functions. Where the exhaustive search defines the notion of subproblems, and the LOF MPF makes the subproblems to have more chances to reuse. As long as two subproblems have the same solution part and they have the same MPF value, they are equivalent and they can be reused. Thus, the number of the equivalent classes of the memoization algorithm is upper bounded by the number of variables times the range of the MPF. And finally, let's see why this template solves the two challenges proposed previously. First, we notice that each of the three parts is just a much smaller program to be synthesized. So we can design synthesizers to solve solve each part. Second, we can control the efficiency of the memoization algorithm with the range of the MPF. By synthesizing an MPF with the smallest range, we can obtain the most efficient memoization algorithm, and thus we can solve the efficiency challenge. To implement a program synthesizer, we generate an exhaustive search from given templates, and to synthesize LOF and MPF, we propose a synthesis procedure that mixes the inductive and the deductive methods. However, due to time limits, we just relegate these details to our paper, and please refer to our paper for details. Finally, the CMEM could be extended to decision problems and counting problems without any change. We evaluate our approach on 40 real-world combinatorial problems and that are collected from Leetcode and national-wide program competitions in China. And our benchmark consists of many classic and important combinatorial problems, and we find that our approach can solve 6 times problems more than previous approaches. That's all. Thank you.
Questions?
Hello. Hi. I'm going to ask a question where I don't know if there is an answer, but I've written papers similar to this myself where we find kind of a nice domain where we can fit with program synthesis. And I see a lot of your examples, like similar to some stuff I've worked on now is Leetcode, and these basically problems that now lots of people are solving. And these days, if you ask ChatGPT to solve one of these problems, chances are it gives you a pretty good solution. So do you think there is a space, and I'm hoping that you give an answer so I can know the answer myself. But where, like, these type of techniques, are there domains that you thought about where these type of techniques will not be able to lose against LLMs and stuff like that? Does the answer make sense?
Sorry, pardon.
Yeah, but I don't know if your experience working on these, if you found out things where you feel like there are problems where, are these problems common enough, essentially, that they will appear beyond problems that everybody solves, like Leetcode or knapsack and so on?
Yeah, we solve problems from Leetcode.
Maybe I can answer this question. I'm the third author. Right. So yes, we have tried ChatGPT, and so it's it's quite impressive. We can give the same millisync specification to it, and it will produce, if you get, say, the knapsack problem, it will produce a perfect answer with perfect explanation. So that's quite impressive, because initially I expected it will only answer nature language queries, but we put millisync specification is still doing it quite well. But the interesting is that if we modify the specification a bit, say the weight is a sum of another 2 variables, so the value is, say, the difference between another 2 variables, then the ChatGPT just gave me a totally random program that I cannot interpret the meaning. So I think the takeaway is that the ChatGPT actually have very good way of match programs, but if we want to adapt the programs, perhaps beyond some limit, it will not work well. Yeah.
So
there's a domain that maybe you could try. I was wondering if you have done any sort of parsing problems, and because they are often dynamic programming problems. And in case you're not already aware, there's a programming language for dynamic programming algorithms called Dyna that you might want to look into and compare if you haven't seen that.
Dyna?
Yeah, DYNA. That's the name of the programming language.
This language can.
I'm not an expert in the language, but I'm just like.
Okay,
But I'm just wondering. The question is, have you tried parsing?
We don't try this language, and I think it would be a very great chance if we can try this in our ongoing work. Yeah.
So how do you determine that a problem is solved? Is it just that the memoization program is generated, or do you actually look at the efficiency of the generated memoization algorithm? So if you synthesize a memoization problem, you generate some code. Do you actually consider the efficiency of this code, like its running time in terms of the inputs?
We check the efficiency manually by ourselves, and we actually apply some inductive program synthesis approach, and the efficiency in the procedure is actually some concrete value, and we can just objective function to be minimized.
Okay, so I also wonder if there's a way to like tell the synthesizers that you want certain values, that you know that certain values will be smaller. For example, in knapsack, there's a capacity and there's the number of items. Can you guide it and say, hey, the capacity can be much larger than the number of items, and therefore the resulting algorithm, I want it to depend less on the capacity and maybe more on the number of items. Is it possible to incorporate that into your synthesizer?
Yeah, currently don't, but I think that's possible. Yes, we can put some weights on the program, say that we just sort these programs. So currently we actually sort this program by their size. So the idea is that the larger the program, because it's a function, then the smaller its range. If you put more function after that, the range will become smaller. So then we prefer the large MPF function first. But then what you said, that we can put another weight function on that. By the complexity, we actually ensure all the generated program are pseudo-polynomial. And in that table, we have just one column just says which of the problem we solve our solution reach the best complexity in theory. That's 31 out of 37 solutions. Okay.